Okay, so for example 2, there are a couple different ways you go about it. Some folks can tell by the way that the terms are defined that this is geometric with a common ratio of 10. Therefore, it will diverge to infinity. Now, if just glancing at it doesn't work for you, then just expand it out. And you don't even have to do very much like simplification, you know? You can be like, okay, well, the first term is 1/3 times 10. And the second term is 1/3 times 10 squared. Third term is 1/3 times 10 cubed, and so on. And I hope it makes sense that like the terms themselves are approaching infinity. So if you add up infinitely many of these values, you're definitely going to get infinity. And so, like so, okay? Let's see, or we could say it diverges to infinity. That might be better. All right, so just remember a sum will converge if it adds up to a distinct finite value, and if it doesn't converge, then it diverges. All right, similar for part B. Part B is not geometric. It is arithmetic though, but you don't really have to know that. Really, you just need to start expanding it out. So they want you to start at 0, and then plug in 1, and 2, and 3, and so on. Again, the terms themselves are approaching infinity, so I hope it makes sense. This one diverges to infinity as well. Whoops. Sorry, every time I lay my hand down. There we go. Okay, part C, there's a couple ways to go about part C. My favorite is just, guess what? If in doubt, yep, expand it out. And then and don't even work very hard at it. So here's what not working very hard looks like in my opinion. So just writing 2 squared over 5 cubed. Like, do I know what 2 squared and 5 cubed are? Yes. Do I care? No. It's actually better for a problem like this to not bother with it. And then just kind of keep expanding terms. It typically takes 3 terms to establish a pattern. So you'll notice I typically will do the first 3 terms at least. Okay, so let's look at this. Is it geometric? Yes. Right? What's its common ratio? What are they multiplying by every time? Well, on the top, they keep multiplying by 2. On the bottom, they keep multiplying by 5. So the common ratio is 2/5. Does that live between -1 and 1? Yes, it does. And so we could say that the sum equals your first term. Here's the lazy version of your first term over 1 minus your common ratio. So then what's that? Well, that would be, oops, that would be 2 squared over 5 cubed over 3/5, which means you're multiplying by 5/3. And then we'll just multiply what's left. So on the top, you've got 4. On the bottom, you have 3 times 25, or 75. So the sum, as n goes from 2 to infinity, of 2 to the n over 5 to the n plus 1 is just 4 over 75. A small number, not, super tiny, surprisingly tiny number for the fact that you're adding up infinitely many terms to get it. Okay, part D. This one, the main thing that you need to know right now is it is not geometric. All you'd have to do is expand it. So you've got 1 plus 1/2. So if it was geometric, you could see if you jump from the first to the second, your common ratio would have to be 1/2, but your third term is 1/3. And so it is definitely not geometric. And then as far as what this one equals, some folks would guess 2, some folks would guess infinity. So I'd say if you guessed anything between 2 and infinity, then you have something that would be like an educated guess. But we're actually going to show that this particular series actually does diverge to infinity. And so as a matter of fact, this is one of our famous sums. The sum as n goes from 1 to infinity of 1 over n. This is called the harmonic series. And it's a special little series because you could see that while the value of the terms do converge to 0. So like at the tail end, I hope it makes sense, whether a series converges or diverges, really what you care about is what happens at the tail end of it. That's what is the deal breaker or maker. And so for this series, the terms do approach a value of 0. Yet we're going to show at the end of this video that it actually diverges to infinity. And then even though the terms converge to 0. So we were going to talk about this more at the tail end of the lesson here. So we'll come back around. Okay, so let's talk about the next concept. And this little example right here should be kind of helpful with not misunderstanding this next concept. So another major idea that goes along with this lesson is what's called the nth term test for divergence. And let's underline the word divergence there. It's so important that you do not ever, not even in your head all by yourself when nobody's listening or looking, it is important that you never call this the nth term test. You will always call it the nth term test for divergence. Yes. Okay. So here's what the nth term test for divergence says, and it is one of the most commonly misunderstood theorems, yet at the same time, if you understand it correctly, it's one of the best little cards you can play for like getting easy answers. Okay, so let's make sure that you understand it correctly. So it says the sum as n goes from 1 to infinity of a sub n definitely diverges if the terms themselves don't converge to 0. So if the limit as n approaches infinity of the terms does not approach 0. All right, and that's the nth term test for divergence. And considering that most of chapter 8 is just all about does something converge or diverge, this is something that will probably kind of like run each series through through this idea before we move on to things that are more difficult. Okay, so let's talk about like what is this saying? So let's say you have a sum, and let's say it's equal to who cares, right? You've got a first term plus a second term plus a third term, and then it keeps going. Well, basically what it's saying is out here, as you go to infinity, if the value of the terms themselves, if they're not approaching 0, then that would mean that at the tail end, you're adding infinitely many values that are not 0. So right? And so I hope that makes sense. Like it's just saying if at the tail end you don't have things that are approaching 0, then your sum is definitely not going to add up to something finite. So hopefully you're okay with that. So this will converge. Or sorry, whoa, wrong word, wrong math word. This will diverge. Diverge for sure. Okay. Hopefully that part makes sense. Okay, so, and then another thing I want you to know, and if you've zoned out, listen to this part because it matters. In chapter 8, it's important that you can look at a series and say whether something converges or diverges, but even more importantly, can you give the correct theory that explains why your answer is the way it is. And when you're tested on the AP exam, that's what they're going to test you on. So you're going to notice that as we move forward, I'm going to ask you to say whether something converges or diverges, and then I'm going to ask you also to give a test that you used or an explanation for what you did, okay? So, for example, for part A, if you were asked right here, if you were asked, well, what's your reason to say it diverges to infinity? Well, since the terms themselves are not approaching a value of 0, you could say, I used the nth term test for divergence. Or that's one reason that you could give at this point. Or another explanation that would be accepted would be to say, hey, it's geometric, but its common ratio was 10. So at this point, you've got two kind of theorems that you could state to explain why you said part A diverges to infinity. And it's this kind of thing that's more important in a way than just getting the answer right. It's being able to explain yourself. Could you have used the nth term test for divergence for part B to say that since the terms don't go to 0, since at the tail end you're not adding up things that are approaching 0, then you'd know it diverges. So I hope it makes sense. Yes, you could have. Could you have used the nth term test for divergence for part C? So it wouldn't take much work to show that the terms do approach 0. Let's look at the nth term test for divergence. It says that your sum will diverge if the terms don't approach 0. Well, what does that mean if the terms do approach 0, like in part C? Well, while the values of the terms do approach 0 in part C, and we did find out that it converged, you would not want to use the nth term test for it, because the nth term test will only tell you when you know for sure that something diverges. It doesn't tell you anything about convergence. A common misunderstanding is people think, and we're going to add this as a caution sign. That says caution in case you can't read my handwriting. I'll give you a little flower and everything. People think that after saying the nth term test for divergence like that, they think that if the limit as n approaches infinity of the terms, if the terms do approach 0, then the sum as n goes from 1 to infinity of a sub n will converge. But the truth is that if your terms go to 0, it doesn't mean anything, because maybe your terms didn't go to 0 fast enough, like we've talked about in the past. And so it turns out that the sum as n goes from 1 to infinity of a sub n could converge or diverge. Could go either way. As a matter of fact, look at the harmonic series. The terms go to 0, but we'll show at the end of this lesson that it actually diverges to infinity. So anyway, so watch out for that. This is important, that not only do you know the nth term test, but you're mindful of what it's not saying. All right, my friends. For example 3, I'd like for you to determine whether each series converges or diverges. If it converges, find its value, and also try to give a reason for why you said it converges or diverges. At this time, your reasons would be one of the following. Either explain it's a geometric with a certain common ratio, or use the nth term test for divergence. See how it goes. Check in with me in the next video.